Okay, so problem 4 is asking about an FM radio station with a frequency of 89.8 megahertz, which uses two antennae that are spaced 8 meters apart. The antennae are driven with the same signal phase. So in the picture, you can see just the two antennae 8 meters apart, and they're each releasing their radio waves, which are interfering. So the red and the red, when those connect, those are going to be constructive, the same with the blue and the blue, but when the red and the blue interact, those are destructive. And the idea is just that when it's red, it's a half wavelength, and when it's blue, it's full wavelength, and when those interact, because they're out of phase, they'll destructively interact, and vice versa for when two things are in phase, they constructively interact. So part A is just asking about wavelength. So we know the wavelength is just always going to be velocity over frequency. So we were given frequency, and we know velocity just from the unit. So all we have to do is plug in those values, keeping in mind that you have to convert megahertz to hertz. So once we do that, we get a wavelength of 3.34 meters. Part B is asking us to find all angles at which there are minima. So the equation for minima, which is going to be where these are destructively interfering, or these radio waves are destructively interfering, is that the path difference equals n plus 1/2 times wavelength, and we're assuming the waves are parallel, so the path difference is just d sine theta. So the problem asks us to find all angles at which there are minima, so we're going to have to figure out what angles there are, like what the max value that n can be, so we can solve for all those angles properly. So we're going to use just the fact that sine theta is going to be in between -1 to 1 before you just get an undefined value to figure out what n can be in this situation. Notably, just this is going to make our math more simple throughout the problem because it's going to stay constant. Wavelength over d is 0.4175. So you can see on the top right, it's set up kind of confusingly, but I'll kind of explain the logic. So once we kind of rearrange the equation, which gets the plus minus 2.4 on one side and the n plus 1/2 on the other side, what you kind of have to do is it's kind of an inequality, so you kind of have to logic through it and solve it separately. So what is, can n be a solid, what integer can n be that fits in between positive and negative 2.4? So using that logic, you can tell that n can equal 0, 1, -1, and -2. So all we have left to do is just rearrange so that d sine theta equals n plus 1/2 times wavelength equation, solve for theta, and plug in the values for all the various places that, or for all the n values. So for n equals 0, theta ends up 0.21. For n equals 1, 0.68. For n equals -1, negative 0.21. And for n equals 2, negative 0.68. So those are locations where there are minima. Part C is just asking about maxima. So the only difference with this is that it's now d sine theta equals n times wavelength rather than n plus 1/2. And we're going to be using pretty much the same idea that we did last time, where we're going to use the fact that sine theta is between 1 and -1 to figure out what n can possibly be. So once we do that, we figure out that n has to be 1, 2, -1, or -2. It's unwritten, but n can also be 0. So using those, once again, we're just going to plug those into our constructive interference equation. Like I said, once again, I forgot to write in that n equals 0. But for n equals 0, theta is just going to be 0. Continuing on, for n equals 1, it's just going to be theta equals 0.43, -1, negative 0.43, 2, 0.99, -2, negative 0.99. So those are the values for which there are maxima for these interfering radio waves. So that's pretty much the problem. I think the confusing thing can be figuring out what n can be, because I think that's where I kind of struggled with, was just finding all the angles rather than just the positive ones, and stuff like that. But yeah, overall, it's not too bad. Thank you for listening.